Okay, I'm going to show you here how to solve inequalities and graph the solution on a number line. Now what you need to understand is the solution to an inequality is just a simpler inequality. Just like the solution to an equation is a simpler equation. Okay, so if that was an equal sign, you would solve this by saying what x is equal to. That's an inequality, so we're going to solve this by showing what x is not equal to and in which direction. Most of the usual rules of algebra apply with one exception. I'll show you the exception in the next question. So for this, all the usual rules of algebra would apply. So I've got 2x is less than 4 plus 6. What did I do? I added 4 to both sides of the inequality, and it remains the same inequality. So 2x must be less than 10, and that makes x strictly less than 5. Now to graph this solution on a number line, x is less than 5. So my number line, I can go 1, 2, 3, 4, 5, 6. Okay, now where is x strictly less than 5? I could go from 4 down, but actually there are other numbers smaller than 5. 4.1, 4.2, 4.7, all those are smaller than 5. So to demonstrate strictly less than 5, we put a circle around the location of number 5. Now this is open. This open circle indicates we don't include 5, but we include everything below it. And so here is our solution. We color in on the number line everything less than 5. And that circle around 5 indicates that everything right up to 4.999, an infinite number of 9s, is all there. See right there, that would be 4.99999. Those 9s keep going, but that circle indicates we don't include 5. There's another sort of standard notation for this, and that is that x is in the set that goes from negative infinity all the way to 5. See that round bracket? That round bracket means we don't include the number 5. It's anything up to the number 5, but not including it. Okay, in the next example, this is very similar to that one, but a little trick comes in that I'm going to explain. So we have negative 3x minus 5x is greater than or equal to negative 7 plus 2. So negative 8x is greater than or equal to negative 5. All right, now we want to divide both sides by negative 8. However, watch very closely. As we do that, so I'm going to do this in steps here. As we divide both sides by negative 8, we immediately switch the inequality. I'll explain that with a simpler example, but here's the rule. If you multiply or divide both sides by a negative, you flip the direction of the inequality. That does not apply with adding or subtracting negatives, but that does apply when you're multiplying or dividing. So here's the rule that makes it different from algebra of inequalities, or algebra with equations. With an inequality, flip the sign whenever you multiply or divide by a negative. So here, when I divide by a negative, I flip the inequality. My solution is that x is less than or equal to, and a negative divided by a negative is a positive, 5/8. So that's just over a half. Less than or equal to 5/8. To plot this solution on a number line, I would have 0, 1/2, 1. And so 5/8 would be right about here. That's 5/8. And notice it's less than or equal to. So I'm going to color that in, and we're less than or equal to that, so I'm going this way. So my solution on the number line is that. And we're including the endpoint, not because that was negative. We're including the endpoint because we're given that sign greater than or equal to, or less than or equal to. That equal sign underneath indicates that we're including our endpoint. So this is everything less than or equal to 5/8. Okay, now this inequality is a quadratic. And to better understand what to do here, I'm going to solve for the roots of this quadratic, and then I'm going to consider the points outside and between the roots as my intervals, and then I'll determine if they're positive or negative and complete the inequality. So basically, if you're solving an inequality involving a quadratic, your quadratic might look something like this. It would have these roots. And if I want to know when is my quadratic greater than or equal to 0, my solution would be for all of these values here and for all of these values here. Because notice here, it's greater than 0, and here it's greater than 0. Here it's less than 0, and here it's equal to 0. So if that was, say, A and that was, say, B, my solution would be for this when x is greater than A, or when x is less than or equal to b. Greater than or equal to A or less than or equal to b. So that's what we're heading towards here. To start out, I'm going to factor this to make things simpler. And so numbers that add to -6 multiplied to 8 would be x minus 4 and x minus 2. So to plot this out, I have roots at 2 and 4. And this opens upward. So my entire quadratic is greater than or equal to 0 for all of these values going this way, or all of these values going that way. When I'm in the middle, my quadratic is less than 0. On the roots, my quadratic is equal to 0, which is what I want, and then to the right of this root and to the left of that root. So my solution here, based on looking at this, and also if I couldn't easily draw the graph, we could plug in a point between them, let's say x at 1, and you'd notice that f at 1 is a negative. So let's say x was equal to, not 1, 3. My apologies. Yeah, let me write that out to make that clear for you. So we've got roots at 2 and 4. And let's consider our function evaluated at 3. If we were to evaluate our function at 3, we would get 3 squared minus 6 times 3 plus 8. And that's going to give us 9 minus 18 plus 8. And that's going to give us a -1. That means that here we're at -1. So you would know that between the roots, f at x is less than 0. You could also put in the number 0, and you'd quickly find that f at 0 is 8, which is positive. Up here we're positive. So if we are to the left of our root, it's positive. And if you put in f at 5, you'd also quickly find a positive number here. 25 plus 8 minus 30 is 3. So f at 5, and you can verify for that for yourself, is 3, which means that if we're over here, we're also positive. Okay, so here's what the answer looks like. X is less than or equal to 2, or x is greater than or equal to 4. Now the word or is important because you cannot be less than 2 and greater than 4 at the same time. So you're either less than 2 or you're greater than 4. That's the full answer. To plot that on a number line, we've got 1, 2, 3, 4, 5. And we're less than or equal to 2. So we're equal. I color it in for equal and then extend that line for less than. So that's less than or equal to 2. And we're greater than or equal to 4. So color in 4. And over here, we're greater than or equal to 4. So this is the full solution here. We want to know when this quadratic is greater than or equal to 0, and it is whenever x is less than or equal to 2, or when it's greater than or equal to 4. We figured that out by factoring, examining the roots, and then looking at the point between the roots and outside of the roots to determine when it's positive or negative to fulfill the criteria. Now I'm going to do exactly the same thing, but with a third order polynomial. Okay, so we're going to apply that same strategy to find out when this thing is less than, strictly less than 0. Okay, so to solve this, I'm going to guess my first root. So it looks to me like a 1 or a minus 1. Well, if we put in a positive 1, that's going to give us 6 plus 1 is 7, minus 5, minus 2, yeah. So that means that 1 is a root, which means I can divide out x minus negative 1. Or sorry, x minus 1. So x minus 1 is a factor because 1 is a root. So I'm going to divide out x minus 1. So I'm going to put a 1 here. I'm obviously going to divide this synthetically because it's faster. If you're not sure how to do this, just watch the video on dividing polynomials and then watch the video on synthetic division to make sense of this. And so what that means is when I divide this, I get x minus 1 times x squared minus x minus 6. And all of that is less than 0. So this is applying synthetic division to factor this into this after first guessing that my function evaluated at 1 gives me 0. So I found that 1 is a root, so x minus 1 is a factor, and then I divided x minus 1 from the rest of this polynomial to get that using synthetic division. Now we're going to factor this. We need numbers that add to negative 1 and multiply to negative 6. So that's going to be negative 3 and positive 2. So all of that is less than 0, which means I've got a third order polynomial with roots at negative 2, positive 1, and positive 3. And because my leading coefficient is positive, I know it goes like this. I don't have any double or triple roots here, so it's going to look like that. You could plug in interval values. I don't really need to here. So my solution is for the third order polynomial to be strictly less than 0, I need x to be strictly less than negative 2, or here, x is between 1 and 3, so x is greater than 1 and at the same time less than 3. That's my full solution. X is less than negative 2, or it is greater than 1 and simultaneously less than 3. So to plot that on a number line, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4. X is strictly less than negative 2, so I'm going to circle it because it doesn't include negative 2. It's strictly less, so here, that's where x is less than negative 2. Or x is between 1 and 3. So I'm going to circle the 1, I'm going to circle the 3, and color in that portion in between. So here's how I would graph on a number line the solution to this inequality.